fuck? How much power's he got?
Some people say Quinn is made out of mud. Poor man's made out of muscle and blood. Muscle and blood and skin and bones. A mind that's a weak and a back that's strong. One time stream, what do you get? Another day older and deeper in debt. St. Peter, don't you call Quinn, cause it can't go goes his soul to the architect's
True. We had to pay another massive bill to the architect yesterday. I don't even know how.
So now we're going to go down to building the model. So we've kind of set these parameters up here. Remember what those are. We've batched and we've shuffled the data set. And again, that's how this works. You can print it out if you want to see what a batch actually looks like. But essentially, it's just 64 entries of those sequences, right? So 64 different training examples is what a batch of that is. All right. So now we go down here and we're going to say build model. We're actually making a function that's going to return to us a built model. The reason for this is because right now we're going to pass the model batches of size 64 for training, right? But what we're going to do later is save this model, and then we're going to pass it batches of 1 pieces of, training, whatever data, so that it can actually make a prediction on just 1 piece of data. Because for right now, what it's going to do is takes a batch size of 64. It's going to take 64 training examples and return to us 64 outputs. That's what this model is going to be built to do the way we build it now to start. But later on, we're going to rebuild the model using the same parameters that we've saved and trained for the model, but change it to just be a batch size of 1, so that way we can get 1 prediction for 1 input sequence, right? So that's why I'm creating this build model function. Now in here, it's going to have the vocabulary size as its first argument, the embedding dimension, which remember was 256 as its second argument, but also these are the parameters up here, right? And then we're going to define the batch size as, batch size none. What this none means is we don't know how long the sequences are going to be in each batch. All we know is that we're going to have 64 entries in each batch. And then of those 64 entries, so training examples, right? We don't know how long each one will be. Although in our case, we're going to use ones that are length 100. But when we actually use the model to make predictions, we don't know how long the sequence is going to be that we input. So we leave this none. Next, we'll make an LSTM layer, which is long short-term memory, RNN units, which is 1024, which again, I don't really want to explain, but you can look up if you want. Return sequences means return the intermediate stage at every step. The reason we're doing this is because we want to look at what the model's seeing at the intermediate steps, not just the final stage. So if you leave this as false and you don't set this to true, what happens is this LSTM just returns 1 output that tells us what the model kind of found at the very last time step. But we actually want the output at every single time step for this specific model, and that's why we're setting this true. Stateful, not going to talk about that one right now. That's something you can look up if you want. And then recurrent initializer is just what these values are going to start at in the LSTM. We're just picking this because this is what TensorFlow has kind of said is a good default to pick. I won't go into more depth about that. Again, things that you can look up more if you want. Finally, we have a dense layer, which is going to contain the amount of vocabulary size nodes. The reason we're doing this is because we want the final layer to have the amount of nodes in it equal to the amount of characters in the vocabulary. This way, every single one of those nodes can represent a probability distribution that that character comes next. So all of those nodes values summed together should give us the value of 1. And that's going to allow us to look at that last layer as a predictive layer, where it's telling us the probability that these characters come next. We've discussed how that's worked previously with other neural networks. So let's run this now. Name embedding dim is not defined, which I mean believes I have not ran this yet. So now we run that and we should be good. So if we look at the model summary, we can see we have our initial embedding layer, we have our LSTM, and then we have our dense layer at the end. Now notice 64 is the batch size, right? That's the initial shape. None is the length of the sequence, which we don't know. And then this is going to be just the output dimension. Or sorry, this is the amount of values in the vector, right? So we're going to start with 256. We'll just do 1024 units in the LSTM, and then 65 stands for the amount of nodes because that is the length of the vocabulary. All right, so combined, that's how many trainable parameters we get. You can see each of them for each layer, and now it's time to move on to the next section. Okay, so now we're moving on to the next step of the tutorial, which is creating a loss function to compile our model with. Now, I'll talk about why we need to do this in a second, but I first want to explore the output shape of our model. So remember, the input to our model is something that is of length 64, because we're going to have batches of 64 training examples, right? So every time we feed our model, we're going to give it 64 training examples. Now, what those training examples are sequences of length 100. That's what I want you to remember. We're passing 64 entries that are all of length 100 into the model as its training data, right? But sometimes, and when we make predictions with the model later on, we'll be passing it just one entry that is of some variable length, right? And that's why we've created this build model function, so that we can build this model using the parameters that we've saved later on once we train the model, and it can expect a different input shape, right? Because when we're training it, it's going to be given a different shape than we're actually testing with it. Now, what I want to do is explore the output of this model, though, at the current point in time. So we've created a model that accepts a batch of 64 training examples that are of length 100. So let's just look at what the output is from the final layer. Give this a second to run. We get 64, 100, and 65. And that represents the batch size, the sequence length, and the vocabulary size. Now, the reason for this is we have to remember that when we create a dense layer as our last layer that has 65 nodes, every prediction is going to contain 65 numbers, and that's going to be the probability of every one of those characters occurring, right? That's what that does at the last one for us. So obviously our last dimension is going to be 65 for the vocabulary size. This is the sequence length, and that's the batch. I just want to make sure this is really clear before we keep going. Otherwise, it's going to get very confusing very quickly. So what I want to do now is actually look at the length of the example batch predictions and just print them out and look at what they actually are. So example batch predictions is what happens when I use my model on some random input example, actually, well, the first one from my data set, when it's not trained. So I can actually use my model before it's trained with random weights and random biases and parameters by simply using model, and then I can put the little brackets like this and just pass in some example that I want to get a prediction for. So that's what I'm going to do. I'm going to give it the first batch, and it shows me the shape of this batch, 64, 100. I'm going to pass that to the model, and it's going to give us a prediction for that. And in fact, it's actually going to give us a prediction for every single element in the batch, right? Every single training example in the batch, it's going to give us a prediction for. So let's look at what those predictions are. So this is what we get. We get a length 64 tensor, right? And then inside of here, we get a list inside of a list, or an array inside of an array, with all of these different predictions. So we'll stop there for this, like, explaining this aspect here. But you can see we're getting 64 different predictions because there's 64 elements in the batch. Now, let's look at one prediction. So let's look at the very first prediction for, say, the first element in the batch, right? So let's do that here. And we see now that we get a length 100 tensor, and that this is what it looks like. There's still another layer inside, and in fact, we can see that there's another nested layer here, right? Another nested array inside of this array. So the reason for this is because at every single time step, which means the length of the sequence, right? Because remember, our recurrent neural network is going to feed one at a time every word in the sequence. In this case, our sequences are length 100. At every time step, we're actually saving that output as a prediction, right? And we're passing that back. So we can see that for one batch, one training example, we get 100 outputs, and these outputs are in some shape. We'll talk about what those are in a second. So that's something to remember, that for every single training example, we get whatever the length of that training example was, outputs, because that's the way that this model works. And then finally, we look at the prediction at just the very first time step. So this is 100 different time steps. So let's look at the first time step and see what that prediction is. And we can see that now we get a tensor of length 65, and this is telling us the probability of every single character occurring next at the first time step. So that's what I wanted to walk through, is showing you what's actually outputted from the model, the current way that it works. And that's why we need to actually make our own loss function to be able to determine how, good our model is performing when it outputs something ridiculous that looks like this, because there is no just built-in loss function in TensorFlow that can look at a three-dimensional nested array of probabilities over, the vocabulary size and tell us how different the two things are. So we need to make our own loss function. So if we want to determine the predicted character from this array, so we'll go there now, what we can do is get the categorical, what's this called? We can sample the categorical distribution, and that will tell us the predicted character. So what I mean is, let's just look at this and then we'll explain this. So since our model works on random weights and biases right now, we haven't trained it yet, this is actually all of the predicted characters that it had. So at every time step, at the first time step, it predicted H, then it predicted hyphen, then H, then G, then U, and so on and so forth. You get the point, right? So what we're doing to get this value is we're going to sample the prediction. So this is just the first time step, actually. We're sampling the prediction. Actually, no, sorry. We're sampling every time step. My bad there. We're going to say sampled indices equals np.reshape. So we're just reshaping this, just changing the shape of it. We're going to say predicted characters equals int to text sampled indices. So it's hard to explain all this if you guys don't have a statistics kind of background a little bit to talk about why we're sampling and not just taking the argument max value of like this array, because you would think that what we'll do is just take the one that has the highest probability out of here, and that will be the index of the next predicted character. There's some issues with doing that for the loss function, just because if we do that, then what that means is we're going to kind of get stuck in an infinite loop almost, where we just keep accepting the biggest character. So what we'll do is pick a character based on this probability distribution. Again, it's hard. It's called sampling the distribution. You can look that up if you don't know what that means, but sampling is just like trying to pick a character based on a probability distribution. It doesn't guarantee that the character with the highest probability is going to be picked. It just uses those probabilities to pick it. I hope that makes sense. I know that was like a really rambly definition, but that's the best I can do. So here we reshape the array and convert all the integers to numbers to see the actual characters. So that's what these two lines are doing here. And then I'm just showing the predicted characters by showing you this. And, the character here is what was predicted at time step 0 to be the next character, and so on. Okay, so now we can create a loss function that actually handles this for us. So this is the loss function that we have. Keras has like a built-in one that we can utilize, which is what we're doing. But what this is going to do is take all of the labels and all of the probability distributions, which is what this is, logits. I'm not going to talk about that really. and we'll compute a loss on those. So how different or how similar those two things are. Remember, the goal of our algorithm in a neural network is to reduce the loss, right? Okay, so next we're going to compile the model, which we'll do here. So we're going to compile the model with the atom optimizer and the loss function as loss, which we defined here. And now we're going to set up some checkpoints. I'm not going to talk about how these work. You can kind of just read through this if you want. And then we're going to train the model. Remember to start your GPU hardware accelerator under runtime, change runtime type GPU, because if you do not, then this is going to be very slow. But once you do that, you can train the model. I've already trained it, but if we go through this training, we can see it's going to say train for 172 steps. It's going to take about, 30 seconds per epoch, probably maybe a little bit less than that. And the more epochs you run this for, the better it will get. This is we're not likely going to overfit here. So we can run this for, like, say 100 epochs if we wanted to. For our case, let's actually start by just training this on, let's say 2 epochs, just to see how it does. And then we'll train it on like 10, 20, 40, 50 and compare the results. But you'll notice the more epochs, the better it's going to get. But just like for our case, we'll start with 2 and then we'll work our way up. So while that trains, we'll actually explain the next aspect of this without running the code. So essentially what we need to do after we've trained the model, we've initialized the weights and biases, we need to rebuild it using a new batch size of 1. So remember, the initial batch size was 64, which means that we'd have to pass it 64 inputs or sequences for it to work properly. But now what I've done is I'm going to rebuild the model and change it to a batch size of 1 so that we can just pass it some sequence of whatever length we want and it will work. So if we run this, we've rebuilt the model with batch size 1. That's the only thing we've changed. And now what I can do is load the weights by saying model.loadWeights tf.train.latest checkpoint directory, and then build the model using the tensor shape 1 none. I know, sounds strange. This is how we do this, rebuild the model. 1 none is just saying expect the input 1, and then none means we don't know what the next dimension length will be. But here, checkpoint directory is just, we've defined where on our computer we're going to save these TensorFlow checkpoints. This is just saying this is the the prefix we're going to save the checkpoint with. So we're going to do the checkpoint directory and then checkpoint epoch, where epoch will stand for obviously whatever epoch we're on. So we'll save checkpoint here, we'll save a checkpoint at epoch 1, a checkpoint at epoch 2. To get the latest checkpoint, we do this. And then if we wanted to load any intermediate checkpoint, say like checkpoint 10, which is what I've defined here, we could use this block of code down here. And I've just hardwired the checkpoint that I'm loading by saying tf.train.load checkpoint, whereas this one just gets the most recent. So we'll get the most recent, which should be checkpoint 2 for me. And then what we're going to do is generate the text. So this function, I'll dig into it in a second, but I just want to run it and show you how this works because I feel like we've done a lot of work for not very many results right now. And I'm just going to type in the string Romeo and just show you that when I do this, we give it a second, and it will actually generate an output sequence like this. So we have Romeo Oskiv, this is the beginning of our sequence, and then it says Lady Capulet, food, maratone, father, gnomes, come to those shall, right? So it's like pseudo English. Most of it are like kind of proper words, but again, this is because we trained it on just 2 epochs. So I'll talk about how we build this in a second, but if you wanted a better output for this part, then you would train this on more epochs. So now let's talk about how I actually generated that output. So we rebuilt the model to accept a batch size of 1, which means that I can pass it a sequence of any length. And in fact, what I start by doing is passing the sequence that I've typed in here, which was Romeo. Then what that does is we run this function generate text. I just stole this from TensorFlow's website, like I've stolen almost all of this code. And then we say the number of characters to generate is 800. The input evaluation, which is now, like, we need to pre-process this text again so that this works properly. We could use my little function, or we can just write this line of code here, which does what the function that I wrote does for us. So char to idx s for s in start string. Start string is what we typed in that case, Romeo. Then what we're going to do is expand the dimensions. So essentially turn just a list like this that has all these numbers, 9, 8, 7, into a double list like this. So just a nested list, because that's what it's expecting as the input, one batch, one entry. Then what we do is we're going to say the string that we want to store, because we want to print this out at the end, right? We'll put in this text generated list. Temperature equals 1.0. What this will allow us to do is if we change this value to be higher, well, I mean, you can read the comment here, right? Low temperature results in more predictable text. Higher temperature results in more surprising text. So this is just a parameter to mess with if you want. You don't necessarily need it. And I've just left mine at 1 for now. We're going to start by resetting the states of the model. This is because when we rebuild the model, it's going to have stored the last state that it remembered when it was training. So we need to clear that before we pass new input text to it. And we say for I in range num generate, which means however many characters we want to generate, which is 800 here. What we're going to do is say predictions equals model input eval. That's going to start as the start string that's encoded, right? And then what we're going to do is say predictions equals tf.squeeze prediction 0. What this does is take our predictions, which is going to be in a nested list, and just removes that exterior dimension. So we just have the predictions that we want. We don't have that extra dimension that we need to index again. And then we're going to say using a categorical distribution to predict the character returned by the model. That's what it writes here. We'll divide by the temperature. If it's 1, that's not going to do anything. And we'll say predicted ID equals, we'll sample whatever the output was from the model, which is what this is doing. And then we're going to take that output, so the predicted ID, and we are going to add that to the input evaluation. And then what we're going to say is text generated.append, and we're going to convert the text that is integers now back into a string and return all of this. Now I know this seems like a lot. Again, this is just given to us by TensorFlow to create this aspect. You can read through the comments yourself if you want to understand it more, but I think that was a decent explanation of what this is doing. So yeah, that is how we can generate sequences using a recurrent neural network. Now what I'm going to do is go to my other window here where I've actually typed all of the code just in full and do a quick summary of everything that we've done, just because there was a lot that went on. And then from there, I'm actually going to train this on a B-movie script and show you kind of how that works in comparison to the Romeo and Juliet. Okay, so what I'm in now is just the exact same notebook we had before, but I've just pretty much copied all the text in here, or it's the exact same code we had before, so we just don't have all that other text in between. So I can kind of do a short summary of what we did, as well as show you how this worked when I trained it on the B-movie script. So I did mention I was going to show you that. I'm not lying. I will show you. You can see I've got bmovie.txt loaded in here. And in fact, actually, I'm going to just show you this script first to show you what it looks like. So this is what the B-movie script looks like. You can see it's just like a long, script of text. I just downloaded this for free off the internet. And it's actually not as long as the Romeo and Juliet play. So we're not going to get as good of results from our model, but it should hopefully be okay. So we just start, and I'm just going to do a brief summary, and then I'll show you the results from the B-movie script, just so that people that are confused maybe have something that wraps it up here. We're doing our imports. I don't think I need to explain that. This part up here is just loading in your file. Again, I don't think I need to explain that. Then we're actually going to read the file, so open it from our directory, decode it into UTF-8. We're going to create a vocabulary and encode all of the text that's inside of this file. Then what we're going to do is turn all of that text, into, the encoded version. We're writing a function here that goes the other way around, so from int to text, not from text to int. We're going to define the sequence length that we want to train with, which will be sequence length of 100. You can decrease this value if you want. You go 50, go 20, it doesn't really matter. It's up to you. That's going to determine how many training examples you're going to have, right? Is the sequence length. Next, what we're going to do is create a character data set from tensor slices from text as int. What this is going to do is just convert our entire text that's now an integer array into a bunch of slices of characters. So that's what this is doing here. Or not slices, what am I saying? It's just going to convert like split that entire array into just characters. Like that's pretty much what it's doing. And then what we're going to say is sequences equals char dataset dot batch, which now is going to take all those characters and batch them in lengths of 101. What we're going to do then is split all of that into the training examples. So like this, right? HELL and then ELLO. We're going to map this function to sequences, which means we're going to apply this to every single sequence and store that in dataset. Then we're going to define the parameters for our initial network. We're going to shuffle the dataset and batch that into now 64 training examples. Then we're going to make the function that builds the model, which I've already discussed. We're going to actually build the model starting with a batch size of 64. We're going to create our loss function, compile the model, set our checkpoints for saving, and then train the model and make sure that we say checkpoint callback as the checkpoint callback for the model, which means it's going to save every epoch the weights that the model had computed at that epoch. So after we do that, then our model's trained. So we've trained the model. You can see I trained this on 50 epochs for the B-movie script. And then what we're going to do is build the model now with a batch size of 1. So we can pass one example to it and get a prediction. We're going to load the most recent weights into our model from the checkpoint directory that we defined above. And then what we're going to do is build the model and tell it to expect the shape 1, none as its initial input. Now, none just means we don't know what that value is going to be, but we know we're going to have one entry. All right, so now we have this generate text method or a function here, which I've already kind of went through how that works. And then we can see that if I type an input string, so we type, input string, let's say, of hello, and hit enter, we'll watch and we can see that the B-movie, trained model comes up with its output here. Now, unfortunately, the B-movie script does not work as well as Romeo and Juliet. That's just because Romeo and Juliet is a much longer piece of text. It's much better. It's formatted a lot nicer and a lot more predictable. But yeah, you kind of get the idea here. And it's kind of cool to see how this performs on different data. So I would highly recommend that you guys find some training data that you could give this other than just the Romeo and Juliet, or maybe even try another play or something and see what you can get out of it. Also, quick side note, to make your model better, increase the amount of epochs here. Ideally, you want this loss to be as low as possible. You can see mine was still actually moving down at epoch 50. You will reach a point where the amount of epochs won't make a difference, although with models like this, the more epochs typically the better, because it's difficult for it to kind of overfit, because all you want it to do really is just kind of learn how the language works and then be able to replicate that to you almost, right? So that's kind of the idea here. And with that being said, I'm going to say that this section is probably done. Now, I know this was a long, probably confusing section for a lot of you, but this is, what happens when you start getting into some more complex things in machine learning. It's very difficult to kind of grasp and understand all these concepts in an hour of me just explaining them. What I try to do in these videos is introduce you to the syntax, show you how to get a working kind of prototype, and hopefully give you enough knowledge to the fact where if you're confused by something that I said, you can go and you can look that up and you can figure out kind of the more important details for yourself, because I can't go into all, the extremes in these videos. So anyways, that has been this section. I hope you guys enjoyed doing this. I thought this was pretty cool. And in the next section, we're going to be talking about reinforcement learning. Hello everyone, and welcome to the next module in this course on reinforcement learning. So what we're going to be doing in this module is talking about another technique in machine learning called reinforcement learning. Now, if you remember at the very beginning of this course, which I know for you guys is probably at like 6 hours ago at this point, we did briefly discuss what reinforcement learning was. Now, I'll go through a recap here just to make sure everyone's clear on it, but essentially reinforcement learning is kind of the strategy in machine learning where rather than feeding a ton of data and a ton of examples to our model, we let the model, or in this case we're going to call it agent actually come up with these examples itself. And we do this by letting an agent explore an environment. Now, essentially, the concept here is just like humans, the way that we learn to do something, say, like play a game, is by actually doing it. We get put in the environment, we try to do it, and then, we'll make mistakes, we'll encounter different things, we'll see what goes correctly, and based on those experiences, we learn and we figure out the correct things to do. A very basic example is, say we play a game, and when we go left, we fell off a cliff or something, right? Next time we play that game and we get to that point, we're probably not going to go left because we're going to remember the fact that that was bad and hence learned from our mistakes. So that's kind of the idea here with reinforcement learning. I'm going to go through exactly how this works and give some better examples and some math behind one of the implementations we're going to use, but I just want to make this clear that there's a lot of different types of reinforcement learning. In this example, we're just going to be talking about something called Q learning, and I'm going to keep this module shorter compared to the other ones because this field of AI and machine learning is pretty complex and can get pretty difficult pretty quickly, so it's something that's maybe a more advanced topic for some of you guys. All right, so anyways, now we need to define some terminology before I can even start really explaining the technique we're going to use and how this works. So we have something called an environment, agent, state, action, and reward. Now I'm hoping that some of you guys will remember this from the very beginning, but environment is essentially what we're trying to solve or what we're trying to do. So in reinforcement learning, we have this notion of an agent, and the agent is what's going to explore the environment. So if we're thinking about reinforcement learning when it comes to, say, training an AI to play a game, well, in that instance, say we're talking about Mario, the agent would be Mario, as that is the thing that's moving around and exploring our environment, and the environment would be the level in which we're playing in. So, in another example, maybe in the example we're going to use below, we're actually going to be kind of in almost a maze. So the environment is going to be the maze, and the agent is going to be the character or the entity or whatever you want to call it that's exploring that maze. So it's usually pretty intuitive to come up with what the environment and the agent are, although in some more complex examples it might not always be clear, but just understand that reinforcement learning deals with an agent, something exploring an environment, and a very common application of reinforcement learning is in training AIs on how to play games, and it's actually very interesting what they've been able to do in that field recently. Okay, so we have environment and agent. Hopefully that makes sense. The next thing to talk about is state. So essentially, the state is where you are in the environment. So obviously inside of the environment we can have many different states, and a state could also be associated with the agent itself. So we're going to say the agent is in a specific state whenever it is in some part of the environment. Now, in the case of our game, the state that an agent would be in would be their position in the level. Say if they're at, X, Y coordinates like 10, 20, they would be at state or in state 10, 20. That's kind of how we think about state. Now, obviously, state can be applied in some different instances as well. If we're playing, say, maybe a turn-based game, actually, that's not really a great example. I'm trying to think of something where the state wouldn't necessarily be a position. Maybe if you're playing a game where you have, like, health or something like that, and part of the state might be the health of the character. This can get complicated depending on what you're trying to do, but just understand the notion that for most of our examples, state is simply going to be location, although it really is just kind of telling us information about where the agent is and its status in the environment. So next we have this notion of an action. So in reinforcement learning, our agent is exploring the environment. It's trying to figure out the best way or how to accomplish some kind of goal in the environment. And the way that it interacts with the environment is with something called actions. Now, actions could be, say, moving the left arrow key, right? Moving to the left in the environment, moving to the right. It could be something like jumping. And an action can actually be not doing something at all. So when we say, agent performed action, that could really mean that the action in that maybe time step was that they didn't do something, right? That they didn't do anything. That was their action. So that's kind of the idea of action. In the example of our Mario one, which I keep going back to, an action would be something like jumping, and typically actions will change the state of our entity or our agent, although they might not necessarily do that. In fact, we will observe with a lot of the different actions that we could actually be in the same state after performing that action. All right, so now we're on to the last part, which is actually the most important to understand, and this is reward. So reward is actually what our agent is trying to maximize while it is in the environment. So the goal of reinforcement learning is to have this agent navigate this environment go through a bunch of the different states of it and determine which actions maximize the reward at every given state. So essentially, the goal of our agent is to maximize a reward. But what is a reward? Well, after every action that's taken, the agent will receive a reward. Now, this reward is something that us as the programmer need to come up with. The reason we need to do this is because we need to tell the agent when it's performing well and when it's performing poorly. And just like we had like a loss function in neural networks when we were using those before, this is almost like our loss function. You know, the higher this number is, the more reward the agent gets, the better. The lower the reward, you know, it's not as good, it's not doing as well. So that's how we kind of monitor and assess performance for our agents, is by determining the almost average amount of reward that they're able to achieve. And their goal is really to, you know, it's almost an optimization problem where they're trying to maximize this reward. So what we're going to do in reinforcement learning is have this agent exploring the environment, going through these different states and performing these different actions, trying to maximize its reward. And obviously, if we're trying to get the agent to say finish a level or, you know, complete the game, then the maximum or like jumping to not for that environment called Q learning, which is actually just an algorithm that we're going to use to implement this idea of reinforcement learning. We're not going to get into anything too crazy in this last module because this is meant to be more of an introduction into the kind of field of reinforcement learning than anything else. But Q learning is the most basic way to implement reinforcement learning, at least that I have discovered. And essentially what Q learning is, and I don't actually really know why they call it Q, although I should probably know that, is creating some kind of table or matrix-like data structure that's going to contain as the, the rows every single state, and as the columns every single action that could be taken in all of those different states. So for an example here, and I'll do one on kind of the whiteboard later on if we can get there. But here we can see that this is kind of my Q table. And what I'm saying is that we have A1, A2, A3, A4 as all of the possible actions that could be performed in any given state. And we have 3 states denoted by the fact that we have 3 rows, and the numbers in this table, or this Q, what do they call it? Q matrix, Q table, whatever you want to call it. The numbers that are present here represent what the predicted reward will be given that we take an action, whatever this action is, in this state. So I'm not sure if this is making sense to you guys, but essentially if we're saying that row 0 is state 0, action 2, A2, this value tells us what reward we should expect to get if we take this action while we're in this state. That's what that is trying to tell us. That's what that means. Same thing here in, state 2. We can see that the optimal action to take would be action 2 because that has the highest reward for this state. And that's what this table is that we're going to try to generate with this technique called Q learning. A table that can tell us, given any state, what the predicted reward will be for any action that we take. And we're going to generate this table by exploring the environment many different times and updating these values according to what we kind of see, or what the agent sees in the environment and the rewards that it receives for any given action in any given state. And we'll talk about how we're going to update that later, but this is the basic premise. So that is kind of Q learning. I'm going to hop on the whiteboard now and we'll do a more in-depth example, but then we're going to talk about how we actually learn this Q table that I just discussed. Okay, so I've drawn a pretty basic example right now that I'm going to try to use to illustrate the idea of Q learning and talk about some problems with it and how we can kind of combat those as we learn more about how Q learning works. But the idea here is that we currently have 3 states, and what is happening? Why was that happening up at the top? I don't know. Anyways, the idea is we have 3 states, S1, S2, and S3, and at each state we have 2 possible actions that can be taken. We can either stay in this state or we can move. Now, what I've done is kind of just written some integers here that represent the reward that we're going to get, or that the agent is going to get, such that it takes that action in a given state. So if we take the action here in S1, right, of moving, then we will receive a reward of 1, because that's what we've written here is the reward that we get for moving. Whereas if we stay, we'll get a reward of 3. You know, same concept here. If we stay, we get 2. If we move, we get 1. And I think you understand the point. So the goal of our agent, remember, is to maximize its reward in the environment. And what we're going to call the environment is this right here. The environment is essentially defines the number of states, the number of actions, and, you know, the way that the agent can interact with these states and these actions. So in this case, the agent can interact with the states by taking actions that change its state, right? So that's what we're getting at with this. Now, what I want to do is show you how we use this Q table, or learn this Q table, to come up with kind of the almost, you know, the model, like the machine learning model that we're going to use. So essentially what we would want to have here is we want to have a kind of pattern in this table that allows our agent to receive the maximum reward. So in this case, we're going to say that our agent will start at state S1. And obviously, whenever we're doing this reinforcement learning, we need to have some kind of start state that the agent will start in. This could be a random state. It could change, but it does need to start in some state. So in this case, we're going to say it starts at S1. Now, when we're in S1, the agent has 2 things that it can do. It can stay in the current state and receive a reward of 3, or it can move and receive a reward of 1, right? If we get to S2, in this state, what can we do? We can stay, which means we receive a reward of 2, or we can move, which means we get a reward of 1. And same thing for S3, we can stay, we get a reward of 4, and we can move, we get a reward of 1. Now, right now, if we had just ran this one time and had the agent stay in each state, like start in each unique state, this is what the Q table we would get would look like. Because after looking at this just one time, starting in each state, what the agent would be able to, or I guess 2 times, because it would have to try each action. Let's say we had the agent start in each state twice. So it started in S1 twice, it started in S2 twice, and it started in S3 twice. And every time it started there, it tried one of the different actions. So when it started in S1, it tried moving once, and then it tried staying once. We would have a Q table that looked like this. Because what would happen is we would update values in our Q table to represent the reward we received when we took that action from that state. So we can see here that when we were in state S1 and we decided to stay, what we did is we wrote a 3 inside of the stay column, because that is how much reward we received when we moved, right? Same thing for state 2. When we moved for state 2, stayed, when we stayed in state 2, we received a reward of 2. Same thing for 4. Now, this is okay, right? This tells us kind of, you know, the optimal move to make in any state to receive the maximum reward. But what if we introduce the idea that, you know, our agent, we want it to receive the maximum total reward possible, right? So if it's in state 1, ideally we'd like it to move to state 2 and then move to state 3 and then just stay in state 3, because it will receive the most amount of reward. Well, with the current table that we've developed, if we just follow this and we look at the table and we say, okay, if we want to use this Q learning table now to, you know, move an agent around our level, what we'll do is we'll say, okay, what state is it in? If it's in state 2, we'll do stay, because that's the highest reward that we have in this table. If that's the approach we use, then we could see that if our agent started in state 1 or state 2, it would stay in what we call a local minima, because it's not able to kind of realize from this state that it can move any further and receive a much greater reward, right? And that's kind of the concept we're going to talk about as we implement and, you know, discuss further how Q learning works. But hopefully this gives you a little bit of insight into what we do with this table. Essentially, when we're updating these table values is when we're exploring this environment. So when we explore this environment and we start in a state, when we take an action to another state, we observe the reward that we got from going there, and we observe the state that we changed to, right? So we observe the fact that in state 1, when we go to state 2, we receive the reward of 1. And what we do is we take that observation and we use it to update this Q table. And the goal is that at the end of all of these observations, and there could be millions of them, that we have a Q table that tells us the optimal action to take in any single state. So we're actually hard coding this kind of mapping that essentially just tells us, given any state, all you have to do is look up in this table, look at all of the actions that could be taken, and just take the maximum action, or the reward that's supposed to give, I guess, the action that's supposed to give the maximal reward. And if we were to follow that on this, we could see we get stuck in the local minima, which is why we're going to introduce a lot of other concepts. So our reinforcement learning model in Q learning, we have to implement the concept of being able to explore the environment not based on previous experiences, right? Because if we just tell our model, okay, what we're going to do is we're going to start in all these different states, or we're going to start in the start state and just start navigating around. If we update our model immediately, or update our Q table immediately, and put this 3 here for stay, we can almost guarantee that since this 3 is here, when our model is training, right, if it's using this Q table to determine what state to move to next, when it's training and determining what to do, it's just always going to stay, which means we'll never get a chance to even see what we could have gotten to at S3. So we need to kind of introduce some concept of taking random actions and being able to explore the environment more freely before starting to look at these Q values and use that for the training. So I'm actually going to go back to my slides now to make sure I don't get lost, because I think I was starting to ramble a little bit there. So we're going to now talk about learning the Q table. So essentially, I showed you how we use that Q table, which is given some state, we just look that state up in the Q table and then determine what the maximum reward we could get by taking, some action is, and then take that action. And that's how we would use the Q table later on when we're actually using the model. But when we're learning the Q table, that's not necessarily what we want to do. We don't want to explore the environment by just taking the maximum reward we've seen so far and just always going that direction. We need to make sure that we're exploring in a different way and learning the correct values for the Q table. So essentially, our agent learns by exploring the environment and observing the outcome/reward from each action it takes in a given state, which we've already said. But how does it know what action to take in each state when it's learning? That's the question I need to answer for you now. Well, there's 2 ways of doing this. Our agent can essentially, use the current Q table to find the best action, which is kind of what I just discussed. So looking at the Q table, looking up the state, and just taking the highest reward, or it can randomly pick a valid action. And our goal is going to be, when we create this Q learning algorithm, to have a really great balance of these 2, where sometimes we use the Q table to find the best action, and sometimes we take a random action. So that is one thing. But now I'm just going to talk about this formula for how we actually update Q values. So obviously what's going to end up happening in our Q learning is we're going to have an agent that's going to be in the learning stage, exploring the environment and having all these actions and all these rewards and all these observations happening. And it's going to be moving around the environment by following one of these 2 kind of principles, randomly picking a valid action or using the current Q table to find the best action. And when it gets into a new state and it, moves from state to state, it's going to keep updating this Q table, telling it, this is what I've learned about the environment. I think this is a better move. We're going to update this value. But how does it do that in a way that's going to make sense? Because we can't just put, the maximum value we got from moving. Otherwise, we're going to run into that issue, which I just talked about, where we get stuck in that local maxima, right? I'm not sure if I called it minimum before, but anyways, it's local maxima where we see this high reward, but that's preventing us, if we keep taking that action, from reaching a potentially higher reward in a different state. So the formula that we actually use to update the Q table is this. So Q state action equals Q state action, and the state action is just referencing first the row, so for the state, and then the action as the column, plus alpha times, and then this is all in brackets, right? Reward plus, I believe this is gamma, times max Q of new state minus Q state action. So what the heck does this mean? What are these constants? What is all of this? We're going to talk about the constants in a minute, but I want to explain this formula actually. So I guess we'll go through the constants. It's hard to go through a complicated math formula. So A stands for the learning rate and gamma stands for the discount factor. So alpha learning rate, gamma discount factor. Now, what is the learning rate? Well, this is a little blurb on what this is, but essentially the learning rate ensures that we don't update our Q table too much on every observation. So before, right, when I was showing you like this, if we can go back to my Windows Ink, why is this not working? I guess I'm just not patient enough. Before, when I was showing you, all I did when I took an action was I looked at the reward that I got from taking that action and I just put that in my Q table, right? Now, obviously, that is not an optimal approach to do this, because that means that in the instance where we hit state 1, well, I'm not going to be able to get to this reward of 4 because I'm going to throw that, 3 in here, and then I'm just going to keep taking that action. We need to, hopefully make this move action actually have a higher value than stay, so that next time we're in state 1, we consider the fact that we could move to state 2 and then move to state 3 to optimize our reward. So how do we do that? Well, the learning rate is one thing that helps us kind of accomplish this behavior. Essentially, what it is telling us, and this is usually a decimal value, right, is how much we're allowed to update every single Q value by on every single action or every single observation. So if we just use the approach before, then we're only going to need to observe given the amount of states and the amount of actions, and we'll be able to completely fill in the Q table. So in our case, if we had like 3 states and 3 actions, we could, 9 iterations, we'd be able to fill the entire Q table. The learning rate means that it's going to just update a little bit slower and essentially change the value in the Q table very slightly. So you can see that what we're doing is taking the current value of the Q table, so whatever's already there, and then what we're going to do is add some value here. And this value that we add is either going to be positive or negative, essentially telling us, whether we should take this new action or whether we shouldn't take this new action. Now, the way that this kind of value is calculated, right, is obviously our alpha is multiplied by this, but we have the reward plus, in this case, gamma, which is just going to actually be the discount factor, and I'll talk about how that works in a second, of the maximum of the new state we moved into. Now, what this means is find the maximum reward that we could receive in the new state by taking any action and multiply that by what we call the discount factor. What this part of the formula is trying to do is exactly what I've kind of been talking about. Try to look forward and say, okay, so I know if I take this action in this state, I receive this amount of reward. But I need to factor in the reward I could receive in the next state so that I can determine the best place to move to. That's kind of what this max and this gamma are trying to do for us, or this discount factor, whatever you want to call it. It's trying to factor in a little bit about what we could get from the next state into this equation so that hopefully our kind of agent can learn a little bit more about the transition states. So states that maybe are actions that maybe don't give us an immediate reward, but lead to a larger reward in the future. That's what this Y and max are trying to do. Then what we do is we subtract from this the state and action. This is just to make sure that we're adding what the difference was in what we get from this versus what the current value is, and not like multiplying these values crazily. I mean, you can look into more of the math here and plug in like some values later and you'll see how this kind of works, but this is the basic formula and I feel like I explained that in depth enough. Okay, so now that we've done that and we've updated this, we've learned kind of how we update the cells and how this works. I could go back to the whiteboard and draw it out, but I feel like that makes enough sense. We're going to look at what the next state is. We're going to factor that into our calculation. We have this learning rate, which tells us essentially how much we can update each cell value by. And we have this, what do you call it here, discount factor, which essentially tries to kind of define the balance between finding really good rewards in our current state and finding the rewards in the future state. So the higher this value is, the more we're going to look towards the future. The lower it is, the more we're going to focus completely on our current reward, right? And obviously that makes sense because we're going to add the maximum value. And if we're multiplying that by a lower number, that means we're going to consider that less than if that was greater. Awesome. Okay. So now that we kind of understand that, I want to move on to a Q learning example. And what we're going to do for this example is actually use something called the OpenAI Gym. Now I just need to throw my drawing tablet away right there so that we can get started. But OpenAI Gym is actually a really interesting kind of module. I don't even really know the way to describe it. Almost tool. It was actually developed by OpenAI, coincidentally by the name, which is founded by Elon Musk and someone else. So he's actually, you know, made this kind of, I really don't know the word to describe it. I almost want to say tool that allows programmers to work with these really cool gym environments and train reinforcement learning models. So you'll see how this works in a second, but essentially there's a ton of graphical environments that have very easy interfaces to use. So like moving characters around them that you're allowed to experiment with completely for free as a programmer to try to, you know, make some cool reinforcement learning models. That's what OpenAI Gym is. And you can look at it. I mean, we'll click on it here actually to see what it is. You can see Gym, there's all these different Atari environments, and it's just a way to kind of train reinforcement learning models. All right, so now we're going to start by just importing Gym. If you're in Collaboratory, there's nothing you need to do here. If you're in your own thing, you're going to have to pip install Gym. And then what we're going to do is make this Frozen Lake V0 Gym. So essentially what this does is just set up the environment that we're going to use. Now, I'll talk more about what this environment is later, but I want to talk about how Gym works because we are going to be using this throughout the thing. So the OpenAI Gym is meant for reinforcement learning. And essentially what it has is an observation space and an action space for every environment. Now, the observation space is what we call our environment, right? And that will tell us the amount of states that exist in this environment. Now, in our case, we're going to be using kind of like a maze-like thing, which I'll show you in a second, so you'll understand why we get the values we do. Action space tells us how many actions we can take when we do the .n at any given state. So if we print this out, we get 16 and 4, representing that the observation space, in other words, the number of states, is 16, and the amount of actions we can take in every single state is 4. Now, in this case, these actions are going to be left, down, up, and right, but yes. Now, env.reset, so essentially we have some commands that allow us to move around the environment, which are actually down here. If we want to reset the environment and start back in the beginning state, then we do env.reset. You can see this actually returns to us the starting state, which obviously is going to be 0. Now, we also have the ability to take a random action or select a random action from the action space. So what this line does right here is say, of the action space, so of all the commands that are there, or all the actions we could take, pick a random one and return that. So if you do that, actually, let's just print action and see what this is. You see we get 0, 2, right? It just gives us a random action that is valid from the action space. All right, next what we have is this env.step in action. Now what this does is take whatever action we have, which in this case is 3, and perform that in the environment. So tell our agent to take this action in the environment and return to us a bunch of information. So the first thing is the observation, which essentially means what state do we move into next. So I could call this new underscore state. Reward is what reward did we receive by taking that action. So this will be some value, right? In this case, the reward is either 1 or 0, but that's not that important to understand. And then we have a bool of done, which tells us, did we lose the game or did we win the game? Yes or no, so true. So if this is true, what this means is we need to reset the environment because our agent either lost or won and is no longer in a valid state in the environment. Info gives us a little bit of information. It's not showing me anything here. We're not going to use info throughout this, but figured I'd let you know that. Now, env.render, I'll actually render this for you and show you. Renders a graphical user interface that shows you the environment. Now, if you use this while you're training, so you actually watch the agent do the training, which is what you can do with this, it slows it down drastically, like probably by, 10 or 20 times, because it actually needs to draw the stuff on the screen. But, you can use it if you want. So this is what our frozen lake example looks like. You can see that the highlighted square is where our agent is. And in this case, we have 4 different blocks. We have S, F, H, and G. So S stands for start, F stands for frozen, because this is a frozen lake, and the goal is to navigate to the goal without falling in one of the holes, which is represented by H. And this here tells us the action that we just took. Now, I guess the starting action is up because that's 0, I believe. But yes, so if we run this a bunch of times, we'll see this updating. Unfortunately, this doesn't work very well in Google Collaboratory, the GUIs, but if you did this in your own command line and you did some different steps and rounded it all out, you would see this working properly. Okay, so now we're on to talking about the frozen lake environment, which is kind of what I just did. So now we're just going to move to the example where we actually implement Q-learning to essentially solve the problem of how can we train an AI to navigate this environment and get to the start, to the goal. How can we do that? Well, we're going to use Q-learning, so let's start. So the first thing we need to do is import gym, import numpy, and then create some constants here. So we'll do that. We're going to say the amount of states is equal to the line I showed you before, so env.observation_n. Actions is equal to env.action_n. And then we're going to say Q is equal to np.zeros, states and actions. So something I guess I forgot to mention is when we initialize the Q table, we just initialize all blank values or 0 values, because obviously at the beginning of our learning, our model or our agent doesn't know anything about the environment yet, so we just leave those all blank, which means we're going to more likely be taking random actions at the beginning of our training, trying to explore the environment space more. And then as we get further on and learn more about the environment, those actions will likely be more calculated based on the Q table values. So if we print this out, we can see this is the array that we get. We've had to build a 16 by 4, I guess not array. Well, I guess this technically is an array. We'll call it matrix, 16 by 4. So every single row represents a state, and every single column represents an action that could be taken in that state. All right, so we're going to define some constants here, which we talked about before. So we have the gamma, the learning rate, the max amount of steps, and the number of episodes. So the number of episodes is actually how many episodes do you want to train your agent on? So how many times do you want it to run around and explore the environment? That's what episode stands for. Max steps essentially says, okay, so if we're in the environment and we're kind of navigating and moving around and we haven't died yet, how many steps are we going to let the agent take before we cut it off? Because what could happen is we could just bounce in between 2 different states indefinitely. So we need to make sure we have a max steps so that at some point, if the agent is just doing the same thing, we can, end that. Or if it's going in circles, we can end that and start again with different, Q values. All right, so episodes, yeah, we already talked about that. Learning rate, we know what that is. Gamma, we know what that is. Mess with these values as we go through and you'll see the difference it makes in our training. I've actually included a graph down below, so we'll talk about that to kind of show us the outcome of our training. But learning rate, the higher this is, the faster I believe that it learns. Yes, so a high learning rate means that each update will introduce larger change to the current state. So yeah, so that makes sense based on the equation as well. Just wanted to make sure that I wasn't going crazy there. So let's run this constant block to make sure. And now we're going to talk about picking an action. So remember how I said, and I actually wrote them down here, there's essentially 2 things we can do at every, step, right? We can randomly pick a valid action, or we can use the current Q table to find the best action. So how do we actually implement that into our OpenAI gym? Well, I just wanted to write a little code block here to show you the exact code that will do this for us. So we're going to introduce this new concept, or this new, you can almost call it constant, called epsilon. And I think epsilon, I think I spelled this wrong. Epsilon. Yeah, that should be how you spell it. So we're going to start, the epsilon value essentially tells us the percentage chance that we're going to pick a random action. So here we're going to use a 90% epsilon, which essentially means that every time we take an action, there's going to be a 90% chance that it's random and 10% chance that we look at the Q table to make that action. Now we'll reduce this epsilon value as we train so that our model will start being able to explore, as much as it possibly can in the environment by just taking random actions. And then after we have enough observations and we've explored the environment enough, we'll start to slowly decrease the epsilon so that it hopefully finds a more optimal route for things to do. Now, the way we do this is we say if np.random.uniform01, which essentially means pick a random value between 0 and 1, is less than epsilon, and epsilon like that. I think I'm going to have to change some other stuff, but we'll see. Then action equals env.actionspace.sample, so take a random action. That's what this means. Store what that action is in here. Otherwise, we're going to take the argument max of the state row in the Q table. So what this means is find the maximum value in the Q table and tell us what row it's in. So that way we know what action to take. So if we're in row, or I guess not row, column. If we're in column 1, that's the maximum value, take action 1. That's what this is saying. So using the Q table to pick the best action. All right, so we don't need to run this because this is just going to be, I just wrote that to show you. Now, how do we update the Q values? Well, this is just following the equation that I showed above. So this is the line of code that does this. I just wanted to write it out so you guys could see exactly what each line is doing and kind of explore it for yourself. But essentially, you get the point. You have your learning rate, reward, gamma, take the max. So np.max does the same thing as a max function in Python. This is going to take the max value, not the argument max, from the next state, right? So the new state that we moved into, and then subtracting, obviously, the Q state action. All right, so putting it all together. So now we're actually going to show how we can train and create this Q table and then use that Q table. So this is pretty much all this code that I have, we've already actually written, at least this block here. That's why I put it in its own block. So just all the constants. I've included this render constant to tell us whether we want to draw the environment or not. In this case, I'm going to leave it false, but you can make it true if you want. Episodes, I've left at 1500 for this. If you want to make your model better, typically you train it on more episodes, but that's up to you. And now we're going to get into the big chunk of code, which I'm going to talk about. So what this is going to do, we're going to have a rewards list, which is actually just going to store all of the rewards we see, just so I can graph that later for you guys. Then we're going to say for episode in range episodes. So this is just telling us, for every episode, let's do the steps I'm about to do. So maximum amount of episodes, which is our training length, essentially. We're going to reset the state, obviously, which makes sense. So state equals env.reset, which will give us the starting state. We're going to say for underscore in range max steps, which means, okay, we're going to do, we're going to explore the environment up to maximum steps. We do have a done here, which will actually break the loop if we've reached the goal, which we'll talk about further. So the first thing we're going to do is say if render, render the environment. That's pretty straightforward. Otherwise, let's take an action. So for each time step, we need to take an action. So epsilon, I think, is spelled correctly here. Yeah, I believe that's right. So I'm going to say action equals env.actionspace. This is already the code we've looked at. And then what we're going to say is next state reward done underscore equals env.step action. We've put an underscore here because we don't really care about this info value, so I'm not going to store it, but we do care about what the next state will be, the reward from that action, and if we were done or not. So we take that action. That's what does this, env.step. And then what we do is say q state action. We just update the q value using the formula that we've talked about. So this is the formula. You can look at it more in depth if you want, but based on whatever the reward is, that's how we're going to update those Q values. And after a lot of training, we should have some decent Q values in there. All right. So then we set the current state to be the next state so that when we run this time step again, now our agent is in the next state and can start exploring the environment again in this current, iteration almost, if that makes sense. So then we say if done, so essentially if the agent died or if they lost or whatever it was, we're going to append whatever reward they got from their last step into the rewards up here. And it's worthy of noting that the way the rewards work here is you get 1 reward if you move to a valid block and you get 0 reward if you die. So every time we move to a valid spot, we get 1, otherwise we get 0. I'm pretty sure that's the way it works at least, but that's something that's important to know. So then what we're going to do is reduce the epsilon if we die by just a fraction of an amount, 0.001, just so we slowly start decreasing the epsilon and moving in the correct direction. And then we're going to break because we've reached the goals, print the Q table, and then print the average reward. Now this takes a second to train, a few seconds really. That one is pretty fast because I've set this at, 1500, but if you want, you can set this at say 10,000, wait another, few minutes or whatever, and then see how much better you can do. So we can see that after that, I received an average reward of 0.288866667. This is actually what the Q table values look like. So all these decimal values after all these updates, I just decided to print them out. And I just want to show you the average reward so that we can compare that to what we can get from testing or this graph. So now I'm just going to graph this, and we're going to see this is what the graph, so you don't have to really understand this code if you don't want to, but this is just graphing the average reward over 100 steps from the beginning to the end. So essentially I've calculated the average of every 100 episodes and then just graph this on here. We can see that we start off very poorly in terms of reward because the epsilon value is quite high, which means that we're taking, you know, random actions pretty much all the time. So if we're taking a bunch of random actions, obviously chances are we're probably going to die a lot. We're probably going to get rewards of zeros quite frequently. And then after we get to about 600 episodes, so you can see that 6 actually represents 600 because this is in hundreds, we start to slowly increase. And then actually we go on a crazy increase here where we start to take values more frequently. So the epsilon is increasing, right? And then after we get here, we kind of level off. And this does show a slight decline, but I guarantee you if we ran this for, you know, like 15,000, it would just go up and down and bob up and down. And that's just because even though we have increased the epsilon, there is still a chance that we take a random action and, you know, get 0 reward. So that is pretty much it for this Q learning example. And I mean, that's pretty straightforward. To use the Q table, if you actually wanted to say, you know, watch the agent move around the thing, I'm going to leave that to you guys, because if you can follow what I've just done in here and understand this, it's actually quite easy to use the Q table. And I think as like a final, almost like, you know, trust in you guys, you can figure out how to do that. The hint is essentially do exactly what I've done in here, except don't update the Q table values, just use the Q table values already. And that's, you know, pretty much all there is to Q learning. So this has been the reinforcement learning module for this TensorFlow course, which actually is the last module in this series. Now, I hope you guys have enjoyed up until this point. Just an emphasis again, this was really just an introduction to reinforcement learning. This technique and this problem itself is not very interesting and not, you know, the best way to do things. About 7 hours of course content, we have reached the conclusion of this course. Now, what I'm going to do in this last brief short section is just explain to you where you can go for some next steps and some further look at a lot of learning, understand machine, a bunch of different, I'm going to suggest point topic, and that's something that's really cool. Play around and see some different things. Going to the TensorFlow website, going to the tutorial page. This is very easy to find. I don't even need to link it. You can just search TensorFlow and you'll find this online. And looking at some more advanced topics that we haven't covered. So we've covered a few of the topics and tutorials that are here. I've just kind of modified their version and thrown that in the notebook and explained it in words and video content. But if you'd like to move on to, say, a next step or something very cool, something I would recommend is doing the deep dream in the generative neural network section on the TensorFlow website. Being able to make something like this, I think, is very cool. And this is an example where you can tweak this a ton by yourself and get some really cool results. So some things like this are definitely happening. Is they just give you the code and brief explanations of why you want to have a firm and leave learning comments. With that being said, again, I hope you enjoyed, and hopefully I will see you again in another tutorial guide or series.